Once again, I'd like to welcome all the participants to Pi Seminar series. Today, it's my pleasure to invite Professor Sid Mishra, who's going to give us a talk on learning PDEs with a particular focus on neural operators. Professor Siddhartha Mishra is a chair professor of applied mathematics at ETH Zurich, where he leads the computational and applied mathematics laboratory. He's also the director of computational science Zurich and a core faculty member of ETH AI Center. His research interests lie in the field of numerical analysis, scientific computing, and machine learning, with applications to different fields of science and engineering, including fluid dynamics, astrophysics, climate science, geophysics, and biology. He's an elected fellow of European Academy of Sciences and a recipient of Collatz Prize of ICIAM, among others. And he's also an invited speaker at the International Congress of Mathematics in Rio in 2018. So over to you, Professor Sid Mishra, for the rest of the talk. Thank you.
So thank you very much. And first of all, I would like to thank Professor Jagtap for the opportunity to speak here. As I was telling him, I am a bit sick and have a little bit of fever and a sore throat, so my voice is not the best, but let's adjust. Okay, so let's start. To begin with, I want to give you a couple of examples, and these days people call this as use cases. First use case is from a tsunami early warning system in the Mediterranean, but it's exactly the same system that exists on the Pacific and in the Indian Ocean. So what happens is that you might have an earthquake, for instance, here just off the coast of Crete in Greece, and because of that, the water gets displaced, sets off a tsunami wave, and the agency, in this case, the Italian Geophysical Agency, has to release a tsunami forecast or a tsunami warning. And that is based on being able to simulate or calculate the values of the wave height at buoys in different locations. For instance, one here off the coast of Greece and one here off the coast of Italy. So based on these wave heights that have been measured here or that are expected to be measured here, they release a tsunami early morning. So what you need here is some more or less real-time understanding, real-time analysis, real-time quantification of how the tsunami waves are going to hit a certain location. So this is one example which comes maybe more from a scientific perspective. The second example is more from an industrial perspective, and this is again another Italian company, in this case Dallara. You might not have heard of it, but they are probably the world leaders when it comes to designing race cars. You know, they work for big companies like Porsche and Mercedes and so on, and they do sort of the most of the design. So what they do in Dallara is that they are interested in designing race cars. And one of the critical elements in the design process is that when you change slightly different parts of the car that I've visualized here, you want to compute or you want to calculate what kind of aerodynamic body forces, drag and lift and so on that you expect. And based on that, how to change different parts so that you can get the best aerodynamic shape. So this is more an example in industry. So we have these two examples, one coming from science and the other from industry. And the question is, how are these problems solved currently? I think all of you know a little bit what's going on here. So the first step is to write down a mathematical model. And often these models, they are expressed in terms of PDEs or partial differential equations, making them essentially the language of nature. Because everything from sort of the smallest scale that you can imagine, the Schrodinger's equation, all the way to the largest scale, that's just the Einstein's equations of cosmology, and everything in between, these are modeled by PDEs. So there's an immense diversity of physical processes, as well as a vast range of spatiotemporal scales. So that's the first step, that you have a PDE which expresses what's going on. The second step, of course, is that we cannot find a solution formula. This is not possible. So instead, what we do is, over the last 80 or so years, is that we have all these numerical algorithms, computational algorithms, on which we approximate PDEs and essentially solve them on a computer. So you have finite differences, finite volumes, finite elements, spectral methods, and so on. And this is an extremely successful, let's say, field, extremely successful area, discipline, and so on. And even in my own lab, the CAM lab here in Zurich, we simulate everything from the core collapse of supernovas to flow past rockets to clouds, tsunamis, and so on, using these traditional numerical methods. So this is a very successful area. So what's the issue? And in particular, for the examples that I started out with, for instance, for the tsunami simulation, you can use what are called shallow water equations and get a very good idea of what the waves are going to be. Similarly, for the race car simulation, you have to use some version of the Navier-Stokes equations of fluid dynamics. So this is a sort of a well-known activity. But what's the catch then, right? My lecture should have finished by now. The catch is, and it comes in several forms. The first form is that it's expensive. These methods are expensive. Even if computers are getting faster and faster, the algorithms are getting better, still the numbers are large. For instance, if you take a simulation of the three-dimensional Navier-Stokes equation at a high resolution, let's say 1000 cubed, then this simulation on a state, not exactly state of the art, but near state of the art system, big high performance computer, supercomputer, it takes approximately 100 hours on a GPU or on GPUs, right? It's multi-node GPUs. On CPUs, this would be 5,000 hours. So already very, very expensive. But the problem is that, okay, 100 hours, one can presumably afford it. But the problem is that many, many problems, for instance, this particular problem, the flow is chaotic. So just making one measurement is not very useful. One simulation is not very useful. What you're interested in is something called uncertainty quantification, where you make statistics or obtain statistical information about the flow. In that case, you need at least 1,000 simulations to begin with, maybe even more. And 1,000 simulations, you see, even this number is very big, right? And if you want to put a dollar cost, this is approximately $500,000, a very, very expensive simulation. The point that I'm trying to make is not just that the PDE simulation is expensive, but it is repeated multiple times. These are what are called many query problems. So if you have uncertainty quantification, like the example that I gave you, or design or inverse problems, this is typically the case. And this is just not affordable, even with the computers that we have. But so in particular, for the examples that I just showed you, even sort of state-of-the-art simulations with uncertainty quantification for the shallow water equations for the tsunami simulation takes more than an hour. And remember that here you needed real-time computations, right? An hour is too long. The wave has already hit where it is where it is supposed to hit. So you need to be much faster here. And the same with the race car design. At the moment per shape, it requires hundreds or thousands of node hours. So if you want to do an iterative design process, this is just too expensive. So the bottom line here is, at least in this context, you need to solve PDEs fast. This is important here. But that's not enough. In fact, as I said, the first step, so this was the second step, the implementation of the numerical methods or the computational cost of the numerical methods. But the first step, which is writing down the PDEs, is not always possible, especially in real world problems, in biology, in geophysics, and especially in environmental science. So if you think of the Earth system, or climate or weather, then it's very clear that the flow of air and water is modeled by the Navier-Stokes equation. Radiation is modeled by the radiative transfer equations. But then you have terms like vegetation, like forest cover, like land, and there are no PDEs that you can write from the first principles which model these interesting physical processes. So either the PDEs, if they're known, are hard to solve, they're expensive to solve, or in many real world situations, they're not even known. So that's where the bottleneck is these days, right? So what we still have though is we have data. For instance, for the Earth system, we have enormous amounts of data. So the question is, can we leverage this data together with the physics and try to learn the solutions of PDEs from data? So that would be my sort of main objective in this talk. So what do I mean by solving a PDE, right? Let's try to understand this. So if you have, the way I think of a PDE is that it's like represents the behavior of a system. For instance, if you take an elliptic PDE like the one here, it's sometimes called Darcy flow or heat conduction equation, steady state diffusion equation. So you can think of it as a system that takes an input and maps to an output. For instance, the input could be the conductivity or the permeability, which is some function here, positive function, and the output could be the solution of the PDE, which is a pressure or a temperature or a voltage, depending on the application that you have. So system taking a input, a function input, and producing a function output. Similarly, you can think of a time-dependent PDE like the compressible Euler equations here of fluid dynamics. And you have the initial conditions function, and what the PDE does is that it evolves and some boundary conditions, of course, but it evolves these initial conditions further in time. So it's a system that takes a function input and provides a function output. And the behavior of the system is characterized by its so-called solution operator, which takes, as I said, a function input and a function output. It's essentially an infinite dimensional object. So when I say learning a PDE, what I mean in this context is to learn the solution of a PDE, or solution operator of a PDE rather, right? And whenever we have to learn, we need some sort of data. We need a data distribution. And this data distribution, I'm just considering the so-called noiseless case. So in that case, you have been given a probability distribution over inputs. This is a probability measure on infinite dimensions. But then you have a solution operator. So it's going to push your data forward like here. And this is the object that you would like to approximate, right? This probability distribution is what you would like to approximate. And you do so with some data. And the data is, we assume that it is given by drawing from the inputs and then evolving the solution operator so that you have these data pairs. Of course, you could also have some noise here, which makes this problem slightly more difficult, but also can be dealt with. So when I say learning a PDE, what I mean is that we have to learn its solution operator, this particular infinite dimensional object, from data. So that is my goal. That's my main objective here. So how are we going to do this now, right? So the answer is, of course, we are in the age of AI. We know that by leveraging compute, by having lots of data, and by using mathematical constructs or objects like neural networks, we should be able to learn things, right? But already at the very beginning, there is a teeny weeny problem that neural networks, whether they're MLPs or CNNs or transformers, these are mappings between finite dimensional spaces. So this could be very high finite dimensional spaces. For instance, images, this could be like millions of dimensions, but nevertheless, these are finite dimensional objects. But it's just as I expressed to you here, the target that we have, the inputs and outputs are infinite dimensional or functions, right? So how do we go between this? We have something which is where what we can do is in finite dimensions, or what we know is in finite dimensions, but our target is in infinite dimensions. So we have to do some sort of a dimension reduction, and this is sort of the core of operator learning, how to do this particular dimension reduction. There are different ways to do it. One way, means, just for definiteness, is to use what is called learn then discretize. This is my own coinage, or own expression, but the idea goes back to many people. But I think it was formalized by Nick Kovacsky and his co-authors from Caltech some years ago. And the idea is, since neural networks are finite dimensional objects, what I need to learn is in infinite dimensions. Can I extend neural networks to infinite dimensions? And it's a straightforward construction if you think of it. So remember, the neural networks are these compositions of elementary functions. And the elementary functions take a vector and produce another vector, right? So, and how do they do that? So the first do a matrix vector multiply. This is the so-called weight matrix. Then they add what is called a bias vector. And then they apply a nonlinearity point-wise or component-wise, if you'd like to see it. This is your activation function. So what Nick and his co-author suggested is that we keep the same structure. We have compositions, but now my inputs and outputs are going to be functions. So you can see that my input is a function. So instead of having a vector that is being added, I add a function. I have to parameterize it in some manner so that I can learn it. The key element, of course, is this matrix vector multiply. And anyone who knows sort of basic function analysis or signal processing knows that the infinite dimensional analog of a matrix vector multiply is this kernel integral operator. So you have an integral kernel and you hit the input against this kernel and integrate. And then they said for the nonlinearity, do exactly the same, make it point-wise and component-wise. So it's a very, very straightforward extension. Of course, the price is that you cannot really write down this or compute this, right? You have an integral, you have functions and so on. So you have to discretize these objects. But first you learn, or you have the machine learning framework, and then you discretize. Once you discretize, it's very clear that there is an issue here of computational complexity. In particular, since we have to discretize my domain D, the complexity of this operation, because the kernel here is, let's say, integral, is essentially quadratic. So if you have 1,000 points in your domain, this is requiring 1,000,000 operations. If you have 1,000,000 points, this will require 1,000,000,000 operations and so on. And quadratic scaling is not very nice. So for computational complexity, we have to make some smart choices. And one particularly smart choice was made by the same group of authors, but now Zhongyi Li was the first author, and it's called a Fourier neural operator or an FNO. So instead of having arbitrary kernels here, they take a translation invariant kernel. So this is a good, let's say, basis to have, right? A lot of physics is translation invariant. And then instead of doing the kernel over physical space, they do it over Fourier space. So what it means is you take a input, take its Fourier transform, multiply a learned Fourier matrix on this. This is your learnable object. Then do an inverse Fourier transform, and the nonlinearity is going to be done pointwise. Okay, so the convolution is in Fourier space, but the nonlinearity is local and in physical space. So that's their construction. And the advantage of this is if you're on a Cartesian domain, then of course this operation, this kernel, the convolution kernel can be done log linear. So it's a huge gain in complexity. And this is one of the reasons why I think FNO is very, very widely used. It's probably the most powerful neural operator, or at least the most widely used one, right? And it's also backed by some solid theory, including mostly from my group, anyway, at the beginning. So this is FNO. But it's not the only way to do this, right? There are other ways. For instance, from my lab a couple of years ago, we proposed what is called a convolutional neural operator or CNO. Here, instead of doing the convolutions in Fourier space, we did them in physical space. And the key innovation compared to FNO was that instead of having a pointwise nonlinearity, like here, we used a pointwise local nonlinearity, we used a non-local nonlinearity. And this is because of some, you'll see in a second why it is. It's based on a very intricate procedure of upscaling and downscaling, or upsampling and downsampling, which allows us to, or which allows us to realize this kind of non-local activation function. And in practice, we of course instantiate this by, because it's you have to stack these layers together. We do it like an UNet, which is a very popular architecture in computer vision, where you take a signal which has many different scales, and then you evolve different scales together and you put them together. So that's the idea. So you have FNO, you have CNO, and there are millions of other neural operators. This is a very, very rich,
Siddharth,
rich.
I have one question.
Yes, please go ahead.
So basically in FNO, when we do the convolution in Fourier space, it is very efficient,
Yes.
right?
Very what?
It is very efficient.
Yes, yes, absolutely.
But now in CNO, you are doing this in physical space. So,
Yes.
so then how efficient, or I would say expensive in terms of,
Yeah, it's
in
actually
comparison
this.
with FNO?
It's even more efficient because now the kernel. So remember that in FNO the kernel is global, right?
Mhm.
So the kernel function itself is global. That's why if you did it in physical space, then it will be quadratic complexity. Here the kernel is going to be local.
Okay,
Okay. So because the kernel is local in physical space, all that you're doing is that you are concentrating on points which are just near the point that you are evolving. So
okay,
it's essentially of linear complexity. It's even more efficient, or it's as efficient, let's put it that way.
okay, okay.
But this is a very, very good question. So it's very efficient because this is why computer vision is based on convolutions, because these are very local objects.
Mhm. Okay,
Okay,
okay.
that's the key principle here.
And one more
Yes,
question, the follow-up question. So basically, when you say convolutions, are you using a structured grid here, or you also
here is a structured grid.
structured grid? Okay,
Okay, I will talk about unstructured grids later, but
okay,
here it's a completely, both FNO and CNO in their original implementations are on a Cartesian grid.
structured. Yeah, yeah.
Okay.
Okay, yeah. Thanks.
Anyway, now let's give you a couple of examples just to see how these things work. So here is a good. I mean, I'll go towards much more realistic examples later, but this is a good academic example because it's not that easy. It's the two-dimensional Navier-Stokes equations on a periodic torus, essentially on a square, but it's at a very high Reynolds number. So that's one thing, and you can visualize it very nicely by looking at the initial vorticity, which is these two shear layers, and then vortices are being shed. So the operator takes the initial velocities and outputs the velocities at a later time. And the architectures are very comparable to each other. Some don't do very well, but most of them do comparable to each other. But what is important now is to look at generalization, because remember, my inputs and outputs are functions, right? They're not necessarily discrete objects. So in principle, I could sample the input and output on arbitrary grid resolutions. So I might have a fixed training resolution, which would be 64 squared. but I should be able to test it out on different grid resolutions, for instance, 128 squared or 32 squared. So if I just took a UNet or a CNN, then you see that the error goes up, means in the sense that it doesn't generalize. It only looks at it as a discrete object and not as a function, the inputs and outputs. As a consequence, the error goes up. FNO was supposed to be designed to sort of keep this error constant and generalize across grids, but actually it doesn't. And in this paper, we also explain why that is not the case, because you can see that the error is not as bad, particularly in this direction, but there is an error. So it doesn't generalize seamlessly. There is a generalization error. Also in this direction, when you coarsen, then there is an error here. And this is because it lacks what is called a resolution or representation invariance property, which was hypothesized or which was explained in this particular paper. CNO, on the other hand, is what is called a RENO, or a representation invariant or resolution invariant neural operator by construction. That's why you see that it has a flat line. There are really, it doesn't matter what grid that you test on, the error is going to be exactly the same. It generalizes very well across grids. And there is a mathematical understanding as well as some practical implications for that. And one of the reasons why FNO is not representation or resolution invariant is because of what is called aliasing. Anyone who knows spectral methods knows this. And you can see that there are these artifacts, high frequency artifacts, which are introduced here, which are not there in CNO. So this is one of the advantages. If you are interested in this particular property, that you want to generalize across grids, which is a reasonable requirement when you are trying to do operator learning. But otherwise, there are many different frameworks. They're sort of comparable to each other. Some places one does well, some cases another one does well. But you have a variety of PDEs that in principle can be solved using, or not solved, but at least learned using these kind of neural operators. But that's not my main objective today. It was only the sort of prelude to my talk, because the main objective of my talk is to find out what are the limitations of this approach and try to find some fixes for that. So the main limitation in my eyes are what are called the sample inefficiency or data inefficiency problem. What do I mean by that? So the same example that I just showed you. Now in this case, we know the ground truth. We have some spectral method that can compute the ground truth. So what we do is that we try to calculate how many samples are necessary in order to get a certain accuracy. How much of training data is necessary in order to get a certain accuracy. And you see that there are three neural operators. There is CNO, there is FNO, and there is also something called the Galerkin transformer. And then we just put it in log-log. So this is not log-log, but this is log-log. So what you see is two things. First of all, there is a consistent decrease in error as the number of training samples increases. This is great because this is what is called the scaling property. And in fact, it was already proved not for these architectures, but for deep nets with George Kaniarakis also in our paper some years ago. So this is a nice thing, that as the amount of training data increases, your error goes down. However, what is bad is the rate and the constant, because you can easily see from here that between 2% and 1%, you require to quadruple the number of samples, right? So this means that the rate is 0.5, which is somehow an upper limit. It's actually worse than that. And this means that we need something like 10,000 samples in order to get 1% error, which is just too much, right? So this is the main difficulty. So in principle, you can, for your problems, learn what is going on, provided that you give enough training data, which is what machine learning is, right? But who is going to give us this data? In 3D in particular, generating data, 10,000 training samples is not a joke, right? It's a lot of compute. So what we need to do is to somehow try to find ways in which this can be done more efficiently. One way which people might think is, hey, you are using a crappy model, right? Maybe CNO, FNO, these are not the right things to look at. Maybe if you change the model, you'll have better scaling performance. In a way, this issue has been discussed and debated in general machine learning for a long time. And in particular, there were these very influential papers out of people who are now the core team of Anthropic, who showed the same results for language models. This was before large language models. This was just language models. And they showed that there are these consistent scaling patterns. However, they realized, or they observed, the transformers were much more data efficient, at least in terms of the constant, if not the rate, compared to LSTM. So LSTMs is a little bit like convolutions for language models, for recurrent systems, right? So this was sort of an encouragement for everyone to go towards transformers. So maybe that's the way. If you go towards operator transformers, then they will be much, much more efficient. Maybe, we'll see. So what is an operator transformer? What is a transformer? So these days, most people know that, but if I will still try to cover it in case someone doesn't know what a transformer is, and I'll only focus on what is called operator transformer, right? And here the root is this mechanism of attention, right? This is the main point about a transformer. So remember that FNO, CNO, these were essentially convolution kernels, right? So these were sort of linear kernel operations. What a transformer does, or attention does, is that it provides a nonlinear data-dependent kernel. So that's the main difference here. And not arbitrary nonlinear kernel, but a very particular nonlinear kernel, which is given by this. Is there a question on the chat? No? Hello?
No, I think it's unrelated. So I think you can continue probably.
Okay, sorry. I just I just saw that someone wrote something on the chat.
Siddharth, can you just repeat this again?
Which one?
The same nonlinear kernel.
Yes, I'm explaining it in a second,
Okay.
right? So see that this is a linear kernel. So you just integrate against a kernel which doesn't depend on the data. It just depends on the spatial coordinates. Here, on the other hand, the kernel itself depends on the data. Okay, that's why it's nonlinear. It's more general, and it's a particular kind of nonlinear kernel. So what you do is there is a complicated expression here, but let me explain with a figure. So to update the value at this point x, so imagine that this is your target point. All that you do is you collect contributions from all the other points in the domain. Okay, just in 1D, all the other points in the domain, and then you weight accordingly. And if you weight with a linear manner, that would be a linear kernel. But what a transformer attention does is that you weigh the contributions of each of these points by an additional operation, which is data dependent. So for instance, the contribution here, you look at some correlations between different points in the domain with this particular, let's say, output point, and then you compute the weight. Similarly here, you do another all-in-one call, compute the correlations, and then pass on. And that's why this is sort of a weighted average. And this weighting is, it's a softmax, it's a weighted average. This weighting is what is computed in this all-to-one calls. So of course, that's good because you get a lot of global information. The problem is that, as you can imagine, there are two all-to-one calls, which means that the entire operation is quadratic in the number of points. Usually people call these as tokens. And it's okay for language because these are essentially strings. But for the situations that we are interested in, 2D, 3D, this is simply not feasible. It's just too expensive, right? So what do we do? Well, this problem has also been there in computer vision, and people, for instance, here at Google in Zurich, they have solved it to some extent by introducing what are called vision transformers. So in vision transformers, it's for those who are familiar with finite volume methods, it's a very, very simple idea. So instead of thinking of all the points on your grid, you have another subdivision. These are these white cells. You can call them as cells. And in computer vision, people call these as patches. So this is just nomenclature. And so what you do is that instead of looking at each point-wise value, you collect several points in the form of these cells, and then you compute a sort of a weighted average, a learned weighted average, which is given as your patch token or patch information. And then you only put attention not between the points, but between the patches. So for instance, this patch and this patch, their correlation is computed. This patch and this patch, their correlation is computed, and so on. The scaling now is no longer based on the number of points because that was just too expensive, but it scales with the number of patches, right, which is much less. In fact, from computer vision, the patch size was always 16 by 16. So they would have an image which might be 256 by 256, and the patches would be 16 by 16. But for scientific applications, this could be a problem, particularly in 3D, because 16 by 16 is probably not is too coarse for us, so this doesn't really solve our problem entirely because it doesn't scale very well that way. So what we rely on finally is another idea that comes from computer vision, which is called windowed attention. And the idea is very simple. It's again a multi-scale, multi-domain process. So what you do is that in addition to patches, you have another level of division or another level of subdivision of the domain. And these are these black boxes, which are called windows. And the idea is that instead of doing this patch-based attention across the entire domain, you just stick to attention inside each window. So this point is only attended to by these points and is not attended to by these points or these points or these points. No more global transfer of information is happening. Okay, then you say, so of course this is computationally very efficient because everything scales according to window size. But then you will say, okay, what's going on here? Because you said that attention is about this global kernel, and now you are making it local again. Means how does that work? So here is where the ingenuity comes in. The point is, and these people, it comes from Microsoft in Beijing, I think, what they realize is that there are these layers, so things are stacked up together. So there's a very simple solution. In this layer, you do this attention operation in each window, and in the next layer, you just slide the windows. So for instance, these two guys which were not attended to are immediately attended to in the next layer. And then you keep on doing this. So because we have this layer-wise construction, there's very nice global information transfer. Okay, so this is the, Ameya, you have a question.
Uh, that actually reminds me about the Swin transformer. If you know this one.
This is what is called Swin transform.
Okay, okay,
So this is the you'll see in a second. So
okay,
this is sort of the basic of a Swin transformer is this mechanism of windowed attention.
okay.
So now there is global information processing, and at the same is precisely the Swin paper. So in addition to that, the shifting of the windows is what gives you the global information processing. This is where Swin comes in, shifted windowed attention, right? So this is the key element, and you still have computational efficiency, right? Because you are just attending to each window in each layer.
Okay.
Now we take this
So
idea.
I have a
Yes,
question. Like in the
yeah, go
previous
ahead.
slide, so basically you are converting the solution into an image format, and there you are using the attention mechanism. Is it correct?
Yeah,
And in the last to last slide, when you introduced the transformer-based operator learning,
yeah.
there you talked about the embedding. So in that case, what are the tokens? Like what are the token embeddings? So is that only image patches, or something else?
No, the image is represented now by some physical variables, right? So
Yes.
this is why this picture is there. So this is not just RGB image. It's, I don't know, a pressure or a temperature or whatever it is. So what you do is that you take each of these patches, which has essentially a vector of physical quantities, temperature, pressure, and so on, and then you lift them into a latent space. You can think of it as some effective coordinates. It's very difficult to give a physical interpretation to them, but think of, instead of having just I don't know, velocity fields, you have stream function, vorticity, and so on, and all these physical quantities are there, or some pseudo physical quantities are there, and this is what provides you the embedding. So each token now represents spatial information as well as physical information coupled together. Okay.
Yeah. Okay.
Yeah, so this is the idea. So now we took this architecture, which is around in imaging and computer vision, and then we just modified it to handle operators. As you can see, one of your questions was also about that. So you take this input. As you can see, there are multiple channels. It is an image-like modality, but it's not images. These are not natural images, right? These are scientific data sets. Then you embed them into some larger latent space. You also do that with CNO or FNO, and then you apply this Swin attention. And this is sort of the basic idea. And you also have this kind of UNet style connection, multiscale information processing. What we're able to prove is that this is a very viable operator learner or operator learning algorithm, neural operator. It can approximate any continuous operator without any problems. So there are some good things about it. But that was not our point, right? Our point was to see whether this will increase the efficiency, right? Whether the sample complexity goes down. And the answer is no. In fact, in some cases, like Poisson equation with Gaussian sources, you see that it does scale better than CNO or FNO. In other cases, it isn't. In fact, later on, you'll see results that this operator transformer is no better than standard neural operators. So this is not the solution here. You can't just use sample complexity, or you can't just use a model to solve sample complexities. There is an issue here. So how can we do this then? There are different ideas, but I think one idea, again, to use an analog from general machine learning, is to realize that if you have GPT or Gemini or whatever, Claude, these days DeepSeek, all of these LLMs or large multimodal models, these are what are called foundation models, right? So what are foundation models? So foundation models, the key is that they are trained on diverse data. So for the context of LLMs, for instance, this could be text or speech or signals or images and so on. All of this is fed to a big neural network, and this is during what is called pre-training. So they're trained to learn some effective representations, and then when they're deployed in specific tasks, for instance, object recognition, they can be locally adapted. So this is the idea behind a foundation model. Foundation model is different from a traditional ML workflow in the sense that it has this two-layered or two-tiered structure. So let me explain what a foundation model for PDEs could look like. And this is one interpretation. Other people have other interpretations. So remember that at the end of the day, you have different PDEs, so heat equation, wave equation, Laplace's equation, Navier-Stokes, so on and so forth, infinitely many of them. For each PDE, you can change the input space. You can have different initial conditions, different boundary conditions, different sources, coefficients, parameters. Each of these measures gives rise to a different operator. So for each PDE, you have uncountable number of operators, and on this direction, you have uncountable number of PDEs. So it's a very, very rich data space. So one notion of a foundation model, one framework for a foundation model can be the following: that your model is pre-trained on several operators which come from different PDEs. This could be one notion here. You'll see an example in a second. And then when it is deployed, so this is the pre-training. When it is deployed, then it can either take a different operator, which is not seen during pre-training from the data set, or it could go for a different PDE, right? So this is the basic idea, that you have this two-layered approach, right? So this sounds well and good if it can be done, but can it work, right? So PDEs are not like text and images. These are well-defined quantities, and if you take a textbook on PDEs, you'll see that there is a chapter on elliptic PDEs, a chapter on hyperbolic PDEs, nonlinear PDEs, parabolic PDEs, reaction diffusion equations, and so on. And these sort of sit in islands, right? There doesn't seem to be a lot of crosstalk among them. So initially, it is justified to be skeptical, because the point is, at any stage, your model can only be trained on a small set of PDEs, because there's a whole universe out there and a fixed number of data distributions. Means it's not like the internet, right? So there's no internet for PDE data. So the question is, can it, from this small set of unrelated PDEs, can it really learn physical representations so that it can generalize later? So this is a question. It's a good question, and we will not find out till we actually do some research on it, till we try to find out. So it is in this process that, let's say last summer or last fall 2024, we came up with a foundation model for PDEs, which realizes this vision, and it's called Poseidon. It looks, many of us are Indians here, it looks a bit like Shiva, but it's the Greek god Poseidon, so who is also the god of nature. So that's the connection here. The code is available, the models are available, or the data is available, and so on. And the idea is precisely to do what I just said. And let me try to explain what it is. So remember that you need a model, but you also need data, because just model is not good enough. So the model here is Scott, the operator transformer. We also tried with other things, but this is the one that worked the best. So that is our first thing. And then what is the data, right? So this is small scale, right? We are not doing chat GPT or something like that. We are not at that scale. We're at small scale. So just to realize the idea, to see whether it works, we pre-trained on 6 operators. So not a lot, 6 operators, but coming only from the equations of fluid dynamics. So this was the Navier-Stokes equation. There were 2 operators, and the compressible Euler equation, there were 4 operators. So there were total of 6 operators from 2 PDEs which come from fluid dynamics. This ended up, because we have a special training procedures called all-to-all training, this allowed us to sort of augment the data. So we have, if you think in terms of images, we have 5 million images. And in terms of token, this is something like 5 billion tokens, which is nothing, because all these LLMs are in the trillions of tokens territory. So we are really small scale. The largest model that we trained had 630 million parameters, which is also not a huge number. We have a model which is like 1.3 billion parameters, 2.5 billion parameters. Hopefully, we'll release it later this year. But still small scale, much larger compared to the scale of most of the scientific machine learning models that are out there, but not huge, right? So that's the information about the model. But remember that it's just pre-training. So it has been pre-trained on this data set, but we don't care about pre-training in some sense. All that pre-training does is to learn useful representations. The key is what happens downstream at the level of these downstream tasks, fine-tuning. How do we fine-tune it? Or what do we fine tune it on, right? So first, we have a data set or a database of 15 tasks corresponding to different kinds of PDEs. Some of them are Navier-Stokes equations, some of them are Euler equations, which are already there in the equations were there, the data sets were not there, but the equations were there in the pre-training database. And then we add like transport to the Navier-Stokes equation, forcing to the Navier-Stokes equation, gravity to the Euler equations. So these are minor physical adjustments or new terms that are added to these equations. And then we have equations like the wave equation, we have the Allen-Kahn equation, Poisson, Helmholtz. These are equations which have not been seen in pre-training at all. So this is a mix. It's like an obstacle course. There's some simpler things that are close to the pre-training data set, and then there are some things which are far away. The question is, how do we do this fine-tuning? It's also very simple. Remember that I have this Scott, so it has two parts essentially. One is an embedding or recovery, which is the dual of embedding. And then we have a latent space where all the operations are happening over the latent space. So instead of sort of training things from scratch, what we do is that we transfer learn. So we keep this latent space fixed, and then for each data set we adjust it, and the embeddings are learned from scratch. This is because how does the equation know? It has been trained on fluid dynamics data, so it knows what pressure is, what velocities are, and so on. Wave equation, for instance, is about displacement of the ground. How does it know that, right? So you have to provide that embedding information, and this is what we do. Hopefully, there is enough physics being learned in these representations. So that's the hypothesis. Did it work? Well, the answer is yes, to some extent. And how do I show you that? Means, of course, I can go through each of the data sets and show you these kind of pictures, but this is just too much. I can show you these kind of scaling curves, which are more useful because what happens as you change the number of data points. Instead, what we do is I'll show you two scores. And please bear in mind what the scores are. So one score is what is called sample efficiency gain. So I fix a baseline, and this baseline is typically FNO because it's the most widely used neural operator. And I compute what is the error for a given task. If I trained FNO from scratch, which is 1,000 data samples. 1,000 was just a number that we use for convenience. And then we look at our model, the fine-tuned model, and said how many samples did it need. So if it needed 100, then this is a gain of factor of 10. If it needed 2,000, then it's a loss of factor of 2, right? So this was one metric that you move along the x-axis. Another metric, which is about error reduction, is you fix the number of samples, 128 just for convenience, and you compute the error with FNO, you compute the error with my model, or any model for that matter, and see how much of an error reduction or an error increase you see. So these scores give you some idea of whether the model is efficient and whether the model is accurate. So that's the basic idea. And let me give you the numbers here. So you can see that there are quite a few gains, but maybe it's even more useful to look at the summary, right? So this is some sort of average scores. And the important thing is that the largest model, it had a gain in sample efficiency on an average of 50, which meant that whatever FNO was able to do with 1,000 samples, on an average median, it required only 20 samples, which is great, right? Because this really solved the sample efficiency. If you can keep this for larger models or for more complex data sets, then this would be a great result. The second, and in terms of the accuracy, you see that it's a factor of 10. For the same number of samples, if there was 20% with FNO, this will give you 2% on an average. Okay. And of course, the results are there in the paper. There are several things that you see from here. First, you see that our models, there are other foundation models. There is one which is from Flatiron, it's called MPP. which barely worked. There's one depot which is from Xinhua and Caltech. This is a good foundation model. We are better, but this was also a good foundation model. And then we had our own sort of CNO based foundation model, which didn't do as well. So what's interesting is that whether you took CNO or Scott, standalone they have exactly the same performance. So it doesn't help if you have convolution or if you use attention. But as a foundation model, there is a huge difference. So transformers are better at sort of pulling information from different sources. Another thing that you see is that as the model size increases, you have a clear gain in performance, right? So that's good because there is some scaling with respect to model size. So these were all very, very interesting results. And just to explain what's going on, let me give you one concrete example, which comes from the Poisson equation. A Poisson equation, you can say, is very simple. Actually, for machine learning models, it's not always that simple. So there's the input, it's a forcing term, and this is the output, which is the solution. Sorry. And what we see is, as I said, it's not the easiest problem for this particular setting, because remember that my pre-training is purely on fluid dynamics data. It has not seen a Poisson equation, right? So my pre-training has been on time-dependent data, whereas I have to fine-tune on a steady-state problem. Pre-training has been mostly on hyperbolic data. Fine-tuning has to be on elliptic. Pre-training is initial conditions to a solution at a later time. Here it is forcing to source term, forcing to solution. And finally, the boundary conditions are different. Pre-training was completely periodic, whereas here it's directly boundary conditions. So this is not an easy task in a way. But yet the model does very well. As you can see, it's much more efficient than FNO and even than CNO, which is very good for elliptic problems. And to understand why it is, we did two experiments. So first, we wanted to see how the latent space behaved, in the sense that we just transferred the latent space. And in another case, we froze the latent space. So now all the physics representations that it has to learn are from the pre-training data set. Of course, you have these embedding parameters and the recovery parameters. The model itself is 160 million parameters. But when you freeze the latent and fine-tune, this is only 300,000 parameters. So it's less than 1% of the model, right? So this is really a small part of the model. Can it learn any physics? Has it learned physics of the Poisson equation from the fluid dynamics dataset? And the results were very surprising. That's why it's worth presenting, that what we observed is that even with one sample, because you see it has been pre-trained on fluid dynamics data. So what would you expect when you give it this kind of problems? That it will give some average fluid dynamics behavior. But actually it doesn't. It starts learning diffusion very, very quickly. In 16 samples, even in one sample, it doesn't look anything like fluid dynamics. So within one sample, it has realized that this is not fluid dynamics. But within 16 samples, it starts diffusing. Even here, when the latent is frozen entirely, still it starts diffusing. And by 128 samples, it gets much better results. So this experiment showed us that there is some useful physical representation that has been learned during pre-training. Otherwise, it wouldn't generalize like this, right? So this was the main point here, and sort of explains a little bit the performance of the model. Of course, needless to say, even a large model is quite efficient. It takes about 4 milliseconds for inference, compared to the data generation time, which is between seconds and minutes in 2D. In 3D is much more dramatic. So this is one way in which I believe that sample efficiency, which is sort of the main driving force, or the main bottleneck rather, of neural operators, can be overcome. And what we show is that there is a feasibility of the PDE foundation models, that these things are not isolated islands, but there are useful physics that are being learned. So even by training on Euler and Navier-Stokes, you can learn something about Poisson equation. And so this was sort of the basic point that we are trying to make. People have already started using Poseidon. There was a very nice paper out of Iowa State where they have this incompressible fluid flow, and they tried different models, and Poseidon actually was the best performing model. So not by us, by someone else. So that's quite nice to know. But this is just the beginning, right? Because there are many caveats. The first caveat is that we do require at least the pre-training and everything has been done on a Cartesian grid. During fine-tuning, you can use complex geometries. This is not an issue. But if you want to genuinely sort of learn on complex geometries, then just using this FNO, CNO type neural operators is not good enough. In the lab, we have graph neural operators, or RIGNO as it is called, multiscale graph neural operators, or transformers that are geometry aware that can do this quite well. There are some good results here. There are a couple of papers. And what we need to do is, of course, to integrate them in our pipeline, in our foundation model pipeline. These are still standalone neural operators. But I want to finish by coming to another problem which is hard to resolve with current neural operators. And that is when you have multiscale physical problems. So for instance, I know Ameya knows this very well. So if you think of the Taylor-Green vortex for incompressible fluid flow, this is how the solution looks like for the spectral viscosity method. This is solution starting from more or less the same initial conditions. And after a while, you get this kind of turbulent behavior. So if I use whatever neural operator, and this one particular one which combines CNO and FNO, we call it CFNO. It's a particularly powerful one. What you see is that you get nowhere close to the ground truth here. What you get is things are completely smeared out. So it has not been able to learn this. There is a good mathematical understanding of why this is the case. So what do we do in this case? What we need to do, and there is a recent paper together with people at Google, is we need to go towards generative AI, because we can't use sort of this kind of discriminative neural operators. And generative AI, the particular form that we wanted is called score-based diffusion models, so conditional score-based diffusion models. And the idea is that for a diffusion model is you learn the probability distribution by denoising. So what we do is that given a clean sample, given the initial conditions and given a clean sample, the forward process produces noise and the reverse process is what produces a clean sample. So this is what the score function is being approximated by, and we sort of implemented that and we were able to obtain results like this. So again, I don't have time for details today. So you see that with a plain vanilla machine learning model, a neural operator, you will never able to resolve this multi-scale behavior. But with a diffusion model, trained end-to-end in this particular case, you have excellent results. You can see it in the spectra, you can see it in the probability distributions, you can see it in things like the Wasserstein metric between the distributions. All these metrics we were able to show. And also there is quite a deep mathematical understanding in the paper where we were able to show that you need to change perspective. You need to go towards diffusion models to be able to deal with this kind of very complex problems. It also works for more realistic flows, not just academic flows like Taylor-Green vortex. This is a nozzle flow, right? Jet flow, and you can see that we were able to resolve it. You can do shock waves, you can do atmospheric flows. And the main promise is, again, time, right? You really save. So for a single sample, it takes you 2 seconds to generate, for instance, this nozzle flow. Whereas with the fastest lattice Boltzmann method that we can have access to, it takes about 4 hours on a CPU, maybe about an hour on a GPU. So this is sort of the main promise. So now I believe that with diffusion and with graphs, you're able to take neural operators to a stage where you can solve more complex realistic problems. And with foundation models, you can solve this pressing issue of sample complexity. So what happens to the use cases? In this case, we do happen to have a lot of data. So the neural operators did very, very well. Means it now takes 1 millisecond, as you saw, to do a 2-dimensional simulation. 3-dimensional is more like 1/10 of a second. This is a little bit coarse, but you get quite good results. And with that, I would like to just come to an end. So my objective was to tell you why operator learning or neural operators are important. And you have different kinds of kinds of operators. You have CNO, you have FNO, you have operator transformers. But for all of them, you have the same problems, that you have sample efficiency, potentially solvable with foundation models. You also need to adapt to different domains, no unstructured grids, point clouds. GNNs is one option, but there are other options. And particularly if you need multiscale computation, statistical computation, then you need generative AI. And together, these things have to be put together, scaled up in order to get good foundation models so that you can really deploy these models in the real world. Okay, so I think with that, I stop here. And thank you very much for your attention. I think I probably took more time than expected, but
I think that's totally fine, Professor. Thank you for an amazing talk. From where you started, and I think you also closed it at that same point with all the new things that you discussed. So I'd like to open the forum for any questions from the participants. Please unmute yourself and you can just ask your question directly.
I think that's the easiest.
Hello. Hi, good evening, Professor. Am I audible?
Yes,
Yep.
yes.
Hi.
You even
so,
come from my home state of Odisha. I can hear it in your voice.
yes.
Yeah.
I'm from
Good.
Odisha. Uh, Now I'm in Israel doing postdoc.
Yeah,
So
perfect. Tell me.
yes. So my question is like, um, means the when we are doing a PDE comes with many parameters, right? A simple PDE like suppose it has 2 or 3 parameters. So when we are trying to solve with physics informed neural network, we fix the value of those parameters and then solve. We get some answer. But again, we want to change the value of those parameter. Again, we just restart it from the start. So is there any method like if we fix those parameters and then training, and in the end like we will get some prediction in some kind of function, so that like exact solution we are getting in numerical solutions, in is it possible that we can get the prediction in functions? I think you get my question.
Yes, absolutely. I got your question. Actually, this is already neural operators automatically takes care of that, because your parameters can be easily fed into the system by. So, for instance, let me give you an example. Maybe let's see. Maybe I have an example here. Okay, I don't know how well you see it. Okay,
Yes.
maybe I have. 'Cause now, of course, it won't work, I guess. Uh, yeah, I know that I have an example somewhere. Yeah, look here. So wave. So this is a wave equation where it's the parameter is actually a function, you know. So you have the entire permeability of the ground, because the waves are propagating under the ground. So there is a layered medium, and you need to give some information about the medium. So so it's not just one parameter; it's a field. So the whole thing is an input to the PD. So this is an example where neural operators, they just you give these two functions, and then they automatically give you an output. So you don't have to worry about parameters, and even if whether it's a foundation model or a standalone neural operator, you can adapt any parameter that you want. For instance, if you have fluid dynamics and the Reynolds number is a parameter, you can easily give it as a channel in your inputs. It could be a constant, it could be a variable, it doesn't really matter. So these are very easy to add to this framework. Okay.
Okay, thank you.
Uh, I have a question. So you,
Go
you
ahead.
said that the foundation models actually solve the sample efficiency problems. So is it because the input source data is coming from different models like FN or CNO? Is that the reason is solving the sample efficiency problem or something else?
Well, this is a very difficult question to answer, right? Because this is why I attempted to give you some intuition into what's going on. So one way you can think of it is that any physical system, its behavior, its response to inputs, its output to inputs, is a complex process, but this potentially can be composed of different elements. Okay, it's very difficult to express it for nonlinear PDEs, but from linear PDEs, probably it's much more easier to express. So, for instance, think of an advection diffusion equation in principle, or think of an ODE with a forcing term, right? A linear ODE with a forcing term. You know that the exact solution has two operators into it. One is the variation of parameters, which is due to the forcing term, and the other is the sort of the evolution, the exponential evolution, which is the matrix evolution, matrix exponential, which is due to the linear term. So now perhaps you don't know both of these terms at one go, but you have learned what a matrix exponential looks like from another data set, and you learned the variation of parameters looks like from another data set. Then your model is able to compose these two, right? These two simple effects, and it doesn't need a lot of parameters to learn this. This is one way of thinking about it, right? That you are able to compose complex physics can be decomposed into simpler steps, And some of these simpler steps are common across different kinds of physics. At least that's what the promise is. That's what the hypothesis is. In practice, it's very difficult to actually show this. This is to demonstrate this. But that is a working principle. Because if not, then this wouldn't work at all. There is absolutely no reason why with just one sample you should not get back, because you should not get back some average fluid flow, right? So there is some physical representation that is useful, that has been learned in this process. But to sort of piece it out, to write down some explicit statements about it, no one is in a shape at the moment. Because it's the same principle for languages and so on, right? So how does ChatGPT work? People have plausible explanations, but no one has ironclad argument, right?
Okay. Another thing, that this diffusion equation, are they sample efficient, or they're not?
By themselves, no. No neural operator is sample efficient. So I can give you the numbers right away. So this is probably with they scale, everything scales, right? This is my theorem with George, but this is like, I don't remember now, 5,000 samples to get these numbers. So here, for instance, this was more like 3,000 samples. This was 3,000 samples, maybe 5,000 samples, something in the order of thousands. Okay. And usually diffusion models need a lot of samples because they have to learn the entire probability distribution. So by standalone, you cannot do this. Maybe as a foundation model, we have not yet integrated this, right? So this very recent work. But once you integrate, we believe that the same sort of transfers also happen there.
Okay.
There was a question on the chat. Okay, nice talk. Thanks a lot.
Professor, are you the diffusion slide which you showed a few moments ago? Is that by any chance a transient problem that you're dealing with?
Yes, everything
Okay.
is transient.
So I have a question in that regard. So when you're so as I think you already implicitly said in your talk as well. So when you have like different sets of PDEs, for instance, like if you are going from maybe parabolic to elliptic or something like that, we know in the transient scenario, I think it's reasonable to say that the information transfer happens unidirectionally, maybe from upstream to downstream, had it been a parabolic scenario, if I'm not wrong. And for elliptic, I think you can happen from all the ways around at every point in the grid. So having something like that, so if you have like two sets of equations, and if you are having data from both of them, which you're using to train your actual model, and then you're wanting to fine tune it for maybe just single one class of those equations, do you think there would be some sort of a bias for the model to deviate to one of them more gently?
Yeah, I see your point, right? But this is precisely tested out in my entire paper, because our
Okay.
model was only trained on not hyperbolic necessarily, because Navier-Stokes has some mixed behavior, but it was really very high Reynolds number. So you can essentially say that these data sets, the pre-training data sets, were really hyperbolic, right?
Okay.
So in principle, you could say that it has learned the hyperbolic behavior to some extent, so it could do wave equation and so on. In that case, it shouldn't work for reaction diffusion equations, and it shouldn't work for Poisson equation. So the point is that it's a little bit more complicated than that. Means even from PDE theory, means you know that this distinction between PDEs is very artificial. It's to teach students. It's not really the case. I can derive even a Poisson equation from Euler equations, right? So there is some deep PDE theory behind it. And so if this was the case, what you were saying is very reasonable. If this would have happened, I wouldn't be learning, then I should have information transfer shown right here, right? Because
Yep.
it's not hyperbolic, so there's no way it should diffuse out.
Yep.
But it does diffuse out, which shows that it is able to latch on to the right kind of physics.
Yes, and probably because and probably this very theory that you mentioned about the PDE, so probably even that is also playing its role in sample
Yeah,
efficiency.
that's absolutely the case. That's why I'm a PDE person. That's
Yes,
why.
and maybe that is, also that is probably why you're also not very clear at this point, like why it is happening, because
Yeah, at the
yeah.
moment, it's a lot of hypothesis. I can speculate more, but that
Okay.
wouldn't be a very useful exercise
Right.
because I don't
Yes.
have the evidence to back my words.
Thank
But
you.
there has to be some mechanism by which information or representations are learned. If
Okay.
not, this will not work.
Sure. Thank you.
I think there is no more question. So
I'm tired.
I really like to thank you, Siddharth, because you are not well still. You gave a really wonderful talk. So I really appreciate that.
Thank you, and all the best to all of you.
Okay.
Ciao.